Good afternoon. We have looked at various factors that affect IC design. Some of it is due to the nature of IC fabrication. We have this process variations, and we anyway will have temperature variations. So those things you have to deal with. Either you have to make your circuit such that it's insensitive to these, or you have to have ways of compensating for them and so on. Okay. And in addition to those, you will have random mismatch, which will cause some effects, mainly DC offset in amplifiers and so on. So you should know how to analyze them. And again, you either have to design them so that these variations are small, or somehow they don't matter, right? Or you calibrate them out and things like that. Exactly what you do with it, it depends on the particular system. But you should at least know what the effect of it is. Okay, so that we know how to do. We know how to calculate the effects of random mismatch. And then there is random noise, which again is inevitable, at least that the thermal noise part, right? Or that white noise in any component that you cannot get rid of. So you can calculate them. Again, you can try to keep the noise level below the required limits, etc., etc. Okay, so that is what you can do. And then in addition to white noise, there is flicker noise, which is not as fundamental, but will anyway be there. So again, you need to know how to calculate those things. Okay. So these are all things that affect you. And if you look at it, actually, you have the signal and you have the signal processing function that you realize, right? It could be an amplifier, it could be a filter. So when you pass a signal through a filter, let's say, it will give you some output corresponding to the transfer function. This process variations, etc., will affect the transfer function, and let's assume that you know how to correct for it. For instance, if the capacitor and resistor values are not what they are expected to be, you can have switches to correct for it, and then get the correct values of capacitors, resistors, etc. Okay, so that you do. But beyond that, as we know, first of all, you will have noise. So that will affect. That's something additional that you get. That will affect the signal, and that's characterized by the signal to noise ratio. You need to have the signal to noise ratio to be more than a certain value in order to go through the signal processing without errors, right? And in addition to noise, you also have distortion. That's what we'll come to, because it's only under this small signal linear approximation that we have linear behavior, right? That's an approximate thing. But in reality, our devices are nonlinear, and you will have nonlinearity. Okay. So now you need to be able to find out how much that is as well. Okay. So because nonlinearity generates, just like noise is not a signal that you put in, but some other signal that gets in anyhow. Similarly, you have nonlinearity that also generates signal that are not in the original signal. Okay. For instance, you know that any linear time invariant system, if you put in a sinusoid at some frequency, you will only get sinusoids at that frequency, okay, which may be altered in magnitude and phase, but you will not get new signals. But with nonlinearities, you can get new signals, you can get harmonics and so on. Okay. But we need to be able to find out how much that is, right? So we'll have nonlinear behavior of components, and we need to find out what the effect of the nonlinearity is. Now, what is the, so far, of course, you are already aware that there is nonlinearity in these components. So what is the measure of nonlinearity that you used to calculate? How did you specify the nonlinearity in any way, right? What did you specify? But yeah, have you calculated this in any of the earlier classes for circuits? What is it that you specify actually? In circuits, what is it? I mean, to say that at least you should only specify, you should only have an input signal of this size. What was it that you were specifying? Swing limits. Okay, so you are specifying swing limits. I'm not sure if there was any class in which you went and calculated how much harmonic comes out of some circuit. Did you? Which one? Huh? Okay. For which circuit is it? Huh? Okay. How do you calculate the harmonics? Yeah. So basically, this swing limit is what we normally use, at least in just to say that you cannot apply signals larger than some value. But it's a very crude thing. It doesn't really tell you how much the error is, right? It assumes that, yeah, it should, the transistor should not go into the triode region and so on. Okay. But it's not as though, like, until the point it goes to the triode region, it will be perfectly linear. And after that, it suddenly becomes nonlinear. That's not how it is, right? So you have to be able to calculate the effect of nonlinearity. Okay. So we can do that with an example. Again, you will see that the method is somewhat similar to how you calculate the effects of noise and mismatch. We will be doing some analysis with some additional sources which represent the nonlinearity. Okay. So just to give you a flavor for it, let's say you are told that you have compound interest of 10% per annum for 3 years. Okay. And the principal is some amount, let's say 100 rupees. What is the actual amount at the end of 3 years? How will you calculate? What do you do? No, I know, but what's the calculation that you have to do? Tell me quickly, what's the amount? If you had to give a really quick and dirty answer, what is it that you would actually calculate? Huh? Yeah, what is that? You'll just calculate the simple interest and then tell me, right? You don't actually compound it because that is linear. Okay. So now you have to refine your answer. What will you do next? Yeah, but what are you doing now? You calculate the interest on the interest, right? That's basically what is it? It's compounding, right? What is the difference between compound interest and simple interest? Simple interest, it only gives you interest on the principal, whereas the compound interest gives you interest on interest. Okay. So this method is something like that. You first assume that it is linear, you calculate everything, and then you have many nonlinear terms of progressive orders, higher orders. You calculate them one by one. So first you assume that you have the solutions from the linear analysis are correct. From that, you calculate the second order inputs, sort of. And from that, you calculate the output. And then from that, you can go to higher harmonics. Okay. So that's basically what you do. In spirit, it is like calculating compound interest by first calculating the simple interest and the interest on the interest and the other further interest on that. Okay. So let's just start with an example that's easier. Now, of course, if this is the circuit, if this is the circuit, you can calculate the output quite easily. It's just a resistive divider. So now let me just call this as R, and let's say that this is some nonlinear element. Okay. And this nonlinear element is given by its IV characteristics. And I'll say that this I is G1V plus G2V square plus G3V cube. It could have higher order terms, but let's stop at 3. In practice also it turns out not universally true, but the higher harmonics keep having like smaller and smaller magnitudes, okay? And you're typically interested in the first few harmonics. As usual, for detailed analysis, you have to resort to a simulator. It's not likely that you'll be calculating the 11th harmonic by hand, by progressively going through the first 10 stages, okay? So now how do we go about calculating this? One is just to write the Kirchhoff's current law. So the current through this, in this case, it's actually a very simple circuit. So we have to write Vi minus V naught by R. This is equal to the current flowing through the two resistors, which is also equal to G1 V naught plus G2 V naught square plus G3 V naught cube. So if you combine this and that, you will get a nonlinear equation in V naught, which you can try and solve. Of course, it's very painful to do. I mean, usually there is no exact solutions to nonlinear equations. You have to solve them by iteration and stop after some time when you feel that the error is small enough. But this is, of course, not what we are going to do. This is quite painful because this is painful enough. And if I add one more component here, let's say if I add a capacitor, I'll also get a differential equation, which makes it even more painful and so on. Okay. So we won't do that. So the first step is to assume that we have only the linear term. Okay. So this nonlinear component is approximated by only the linear term. So in this case, we have only one nonlinear component. I'll say I equals G1 times V. Okay. So if I use this, what will be V naught? What is it? Yeah, it's just a resistive divider, right? You have a resistor 1 by G1, you have a resistor R, it's a division between the two. So V naught will be 1 by 1 plus G1 R times Vi. Okay. So again, usually it is with specific inputs that we calculated. I mean, general expressions you can do, but I mean, anyway, it's kind of painful. So now, and one of the common use cases is to find out harmonic distortion. When you have a sinusoid, you should get sinusoid at the same frequency, but you will also get harmonics. And the strength of that harmonic relative to the fundamental is a figure of merit. Okay, so it's called the harmonic distortion. And if you sum up all the harmonics, it's the total harmonic distortion and so on. So let's say the input is some sinusoid. What will be the output? It will just be some fraction of the same okay. And this one, let me just to simplify the notation, I'll call this amplitude as VOP1. Okay, so this is what we get from first order analysis. This is the peak value times cos omega t. Okay. Now, of course, if I add a capacitor or some other inductor or something, you won't get cos omega t. You will also get some phase shift, but the principle remains exactly the same. Okay. So now in step 2, what we do is the following. We will use the solution from step 1. Okay. So across this nonlinear element, I'll assume that the voltage is what I solved for in step 1, VOP1 cos omega t. Okay. And now my I is given in terms of these, right? So I will be So V across this will be that, and the current through the element will be G on VOP1 cos omega t. This part I've already taken into account when I did step 1. In fact, this is what I used to get the solution of step 1, plus G2 VOP1 square cos square omega t plus higher order terms. Okay. I'll just stop now at the second order term in the second step. So now what can this be represented as? So I have only these two. Okay. Now, this first order term can of course be represented as a resistor whose conductance is G1. Okay. And the second order term is now represented as an additional current source. This you now see the common theme, right? Any error can be represented as an additional source. In this case, I have expressed current as a function of voltage. So the additional source is also a current source. So now this current source has a value G2 VOP1 square cos square omega t, which is that. Okay. So you can clearly see now the nonlinearity is itself adding a second harmonic current. Okay. Now you think of this as an incremental source compared to before, right? Our original input is only the cos omega t source in Vi. Now we think of this as an additional incremental source and continue with linear analysis. Okay. So you calculate the second order term, and the second order term and then you do linear analysis with the incremental with the new source. Okay. What is the circuit now? So we are only doing incremental analysis. That is whatever is on top of this. So this Vi will be 0. We will only do it with the additional source. Okay. So the new circuit that we have to solve for is, it has this R and a conductance G1. It should be obvious from the symbol whether I'm writing the conductance or the resistance. And then we have this new source, which is G2 VOP1 square by 2, 1 plus cos 2 omega t. Okay. So if I call this, maybe whatever I called in, whatever I got in step 1, I could call it VO1, whatever comes out as first order. Now I'll solve for VO2. Okay. So what will be VO2 in this case? Again, this is quite simple, right? What will it be? And what do you have to do? What you have a current source and you have two resistors. That's all. So what is it that you get? Yeah, it's basically VO2 is this current source times the effective resistance, which is What is it? R by 1 plus Rg1. Okay. Right? So actually minus, I mean, you have to mind the polarities of these things. So it is minus that, right? So you have this as the solution from the second step. Okay. So what does it do? If you look at, if you stop here, let's say, in fact, the nonlinearity, if you assume that it had only two orders, like the first order and the second order term, we would stop at this point. Okay. What is the additional stuff that you get? First, there are two terms here. One is the first term here is constant, right? So that's like a DC offset term, and that is characteristic of even order nonlinearity. It's only when you do even order. If you remember the trigonometric expansions, if you have even powers of cos or sine, you will have a constant term. If you have odd powers of cos or sine, you will not have that, right? So this DC offset, this DC shift is characteristic of even order nonlinearity. I mean, that's just a aside, but anyway, that's what you will see. So what happens is you will see some shift in the DC operating point, and then you will also see a second harmonic term. Okay, so the second harmonic term you will get it as the expressions can look messy. In fact, if I expand out the expression for VOP1, it will look even more messy. But you get the idea. That is the more important thing, right? You can go through the calculations to get this. So you have a second harmonic term also here. And if you want to, you could specify, typically harmonic distortion is specified as amplitude of the second harmonic divided by the amplitude of the fundamental. Okay. And if you want it in dB, you take 20 log to get you the answer in dB. Okay. If you buy audio amplifiers and so on, you will see total harmonic distortion either specified in percentage or in dB or something. Okay. So again, basically the one thing that you need to know for career in circuit design is linear circuit analysis. If you know that, everything will reduce to linear circuit analysis. We won't analyze something more complicated than that because it's actually too difficult. Well, our goal is to get insights into circuit design, but you can see that distortion analysis, noise analysis, mismatch analysis, all of them are about the same. With every element, you will get some additional source, and with that additional source, you have to be able to carry out the analysis. Okay. Any questions so far? So now you can see that you can, at least this is doable. While this has many steps and may take time, this is doable. You can have capacitors, then you have to, it's still linear analysis. You do the Laplace transform analysis. Only thing is, at every step, you have to keep track of frequency, right? So for instance, in the first step, you do Laplace transform analysis and you get some expressions of S. What is that actually? What does it mean? I mean, you calculate something as a function of S. What does it really mean? What will I see in the lab when I measure things? So when I do Laplace transform analysis, I say that something is a transfer function h of S and Vi is, let's say, Vp cos omega t. What is it that actually comes out if I measure in the lab? What will I get out? This h of S is some complex function. This Vi is something that I can see on an oscilloscope screen. So what will I see if I do this experiment in the lab and put the output to the oscilloscope? What is it? What will I see? No, it's only for LTI systems that you can write h of S, right? That is for sure. So basically, you will get a sinusoid, and this transfer function tells you the magnitude and phase of that sinusoid. So what you will get out will be Vp h and this has to be evaluated at j omega cos omega t plus angle of h at j omega. Now this is of course routine. This is why we use the frequency domain analysis turns differential equations into algebraic equations. It makes the analysis easier. That's why we use it. But this is basically what you will see. If you apply a sinusoid, you will get that sinusoid. Now in this distortion analysis, of course, you have to do it properly. In the first step, you can use Laplace transforms if you have capacitors, inductors, and so on. S will be j omega. In the second step, the excitation is at 2 omega. So then you substitute S with j times 2 omega. Okay. So you have to do that properly, keep track of it so that you get the time domain expressions. Because this nonlinearity, this can be calculated from the time domain expressions, right? Okay. So in the second step, you can do Laplace domain analysis, but then you substitute S equals j to omega and so on. Is that fine? So now we know we can calculate the second harmonic. What next? So let's say my nonlinearity has higher order terms also, or maybe not. But should we stop here, or what is the next step? Huh? Okay, so clearly if I have the third term G3 V cube, I will have to add that term, right? That seems easy. I mean, just like I introduced the current source here, which was G2 V square, I will have to introduce G3 V cube. Is that all, or is there something more? So you tell me, what should I do? So one is, I mean, taking this basically just like I did G2 times VO1 square, I will have to take G3 times VO1 cube. So that part is clear. But is that all, or is there something else? Yeah, should we? If so, why? If not, why not? It's not about accuracy. So let's say we had only 2 orders, right? Huh? Yeah. Which we take it. Which one will we get out of? No, we've already taken. Oh, you mean this one? Okay. So let's say that our nonlinearity had only 2 terms, G1V plus G2V square. Should we stop here, or is there something more to calculate? Stop. Okay, what should I calculate? Huh? How? Yeah. So the nonlinearities can interact. I mean, the element has only second order, but when you have this R and that combination, you can have third order nonlinearity from that. Okay. Because if you go to the next step, so let's say we had only 2 terms, right? What do we have so far? After the second step, we have the output to be equal to VOP1 cos omega t plus VOP2 cos 2 omega t. Basically, this VOP2 is an abbreviation for this whole thing. Okay. Plus, I also have some DC offset. Okay. Let's say I ignore that for now. Okay. Now, if I still had only 2 nonlinear terms, I would have G1. This is V02, right? This is the linear term plus G2 V02 square, which is VOP1 cos omega t plus VOP2 cos 2 omega t square, right? What will this give you? So first of all, it gives you the individual squares will give you the second harmonic and the fourth harmonic. Okay. But let's say we are not even interested in that. But it also gives you third harmonic. The cross term will give you third harmonic, right? So you will get VOP1, VOP2 times the cross term gives you cos 3 omega t. There are many other terms, but if you are interested in the third harmonic, you still have to calculate this. Okay. So you can see, I mean, this thing kind of quickly grows. If you have many terms, basically there are lots of cross products and so on. So let's say we at least want a first order estimate of the second harmonic term and the third harmonic term. The second harmonic term will come from step 2. The third harmonic term should come from step 3, but step 3 should also include the second order nonlinearity. Okay. Is this clear? So you can get third harmonic or third order term from two different ways. And of course, you have the other one, VOP1 cos omega t cube. If you did have this term, you will anyway get the third harmonic, right? You will get basically VOP1 cube by 4 cos 3 omega t, right? From that. So you can get third harmonic from the third order nonlinear term and mixing of first and second order nonlinear terms in the second order nonlinearity. Okay. Is that fine? Which one? Which is 3 by 2 omega? Hey, no. How will you get that? What is cos omega, cos theta times cos 2 theta? What terms do you get? No. I mean, half is in the coefficient, not inside the argument, right? If you mix like second, I mean, if you mix omega and 2 omega, you will get 3 omega and omega. Not 3 by 2 omega. That half comes in the coefficient that I've already taken into account, right? It is 2 VOP1, 2 VOP2 divided by 2. What is it? Cos A, cos B. Half is outside, right? Right? Okay. So now, if you want to calculate the third order term, you will have to consider an incremental input, which is like this. We have G, I mean, we have, sorry, this was what I called R1. And this part is 0. We have an incremental input because of the second order term, which is G2, VOP1, VOP2. First of all, what was it? This, yeah, okay, this is fine. I abbreviated the whole thing anyway. So, cos 3 omega t plus G3 VOP1 cube by 4 cos 3 omega t. I'm just showing it with sinusoids because it is, they are familiar. But of course, you can do this with complex exponentials, take the real part, and so on. Okay. So this this term comes from third order nonlinearity. This term comes from second order nonlinearity. So even if your nonlinear element has only second order term, in the circuit you can have any order harmonic. Okay. But of course, typically we calculate only up to, if at all we do it by hand, we do it up to the third harmonic and stop there. The main point is to know that it can be calculated, right? That is actually again another important aspect of being a designer. So somehow or the other, you have to calculate. Okay. So the calculation may be approximate, may be very crude, because you will always come to some situation where, I mean, you will see some phenomenon that you didn't anticipate. Okay, so maybe you didn't anticipate any harmonic, but it is there. Now, you can throw up your hands and say, I have no idea why this is happening. Or you can try to crudely model some phenomena, see if it corresponds to that. Okay. So you will of course have simulators, but the simulator is very complex. So it gives you some harmonic. You don't know what it is because of. So for that, you will need to do analysis. And actually, one of the very important things is to just believe that anything that is there, you can calculate. Okay. So maybe you will have to learn some algebraic technique. Maybe you will have to like spend a lot of time. But if you believe that you can calculate, you will find out ways. And the first way today is, of course, go search the internet. I mean, somebody else would have done this and put it on the internet. But even if they have not, maybe you can invent something new. Okay. So it's very, very important because you can't say that this cannot be calculated. Maybe a very crude approximation can be calculated. And yes. Right, correct. So that will happen. So the amplitudes that you calculate for each one can be different. Okay. So what he is talking about is that this is not the only mixing product, right? Here, the mixer, this combination, when you square it, what all will you get? If you square this, you will get 2 omega and DC. If you square this, you will get 4 omega and DC. And if you mix these two, you will get 3 omega and omega. That means that you already had some amplitude for the component at omega, and that amplitude has to be corrected. And that's true of the third one also. This gives you 3 omega and omega. Okay. But let's say that we at least try to calculate the most important term for each harmonic, right? For the fundamental, I already calculated in step 1. Maybe I'll have to refine it. I will have to. In fact, if you're, I don't know at what point you are in RFIC design, those of you who are taking it, you know about compression. Have you heard of this? What is that? That's basically a correction of the fundamental amplitude because of nonlinear terms, right? Probably you only took the third order term, but it will happen here also. This second order will give you the third order one. What happens is when you pass it through a nonlinearity, you calculate the first order term, the fundamental component, using the small linear equivalent circuit. You will get some amplitude. But higher order nonlinearities can also give you the fundamental term. And that correction is what usually comes out as compression, okay, or sometimes expansion, okay. So that's what it is. So you can go on refining it, but what we have done is at least we only calculated what is qualitatively new. If you calculate only using the small signal linear equivalent circuit, you will say that, oh, this has only sinusoids at omega. Now we need to know sinusoid at 2 omega, that we calculate at the first step. That amplitude is also not correct, right? If you go through the further steps, you will get further refinement of that amplitude. Similarly for 3 omega and so on, okay? But the thing is, at least in what are called weakly nonlinear circuits, this term is more significant, this is less significant, and so on. So if the nonlinear terms are less significant than the linear term, this progressive corrections will also be successively smaller, okay? So qualitatively, we may still be okay, right? And also we have to be a little careful about what we mean by accuracy. That is, there is qualitative accuracy and there is quantitative accuracy. So let's say this is my approximate answer, and the actual answer happens to be this in one case. That in the other case, right? In one of the cases, the answer was supposed to be 1.1 cos omega t, but I did some crude calculation because I was lazy, and then I got 1 cos omega t. The other one, the actual answer is 1 cos omega t plus 0.001 cos 3 omega t. But again, I approximated as 1 cos omega t. So which is now a better approximation? Where am I closer? It's hard to tell, okay? The first one, of course, I have changed the amplitude, but that may not be the most serious error. In the second one, if I claim that I have only 1 cos omega t, if I calculate the percent error, obviously the second one has a smaller percentage error, right? Because the error amplitude is smaller. But this is telling you qualitatively something different, okay? So qualitatively, I would say it's more important to get the second one than the first one. Second one, I recognize that there is a third harmonic. The first one, I don't even know that. Okay, even if I calculate it accurately, I don't know that there is third harmonic. So when you're doing hand calculations, sometimes you may carry out very crude calculations, but what you are looking for is sometimes modeling qualitatively what is happening. Okay. So even if you get, let's say, only 50% of the third harmonic, but you recognize that there is third harmonic because of this phenomenon, that will be important. Okay. Of course, the more accurate the calculation, the better it is always. Okay. So what this whole thing allows you to do is to calculate something, right? We had nothing, which is linear analysis, or swing limit, which simply says you can't apply a signal larger than this, then you will be finished or something like that. This one at least tells you if you want your harmonic to be less than, let's say, 1% of your fundamental amplitude, what should be the signal amplitude? Yes? Yeah. So again, how accurately you want to calculate it. So if you are explicitly asked to calculate the compression, this gain compression and gain expansion is something that happens with nonlinear circuits. Are you taking RFIC design? So anyway, it's not. So basically, if you plot the fundamental output versus fundamental input, I mean, the input has only the fundamental. The linear analysis says that it should just be a straight line, right? Now, because of nonlinearity, the other terms can, for very small amplitudes, it will follow this. For larger amplitudes, it can do that, or it can even do that. Okay, depending on the nonlinear term, the sign. Okay, so if you are explicitly trying to calculate that, yeah, of course, you have to go through further steps. If you only want the linear part, then I think stopping at the first step is fine. Okay. No, it's the fundamental component. By the way, these are all measured with sinusoids, right? It's the amplitude of that at the fundamental. That extra error, whatever you get from the higher order, could be called compression or expansion. That's what it is. What do you mean by two nonlinear terms? You mean multiple nonlinear elements? Oh, yeah. In it, it's the same. Multiple nonlinear element. Step one, you take the linear terms of all of them, calculate. Step two, you calculate the second order terms of all of them from the corresponding first order terms, right? Maybe I have 2 or 3 different resistors like this, right? I could have in the first step, I calculate V1 of 1, V2 of 1. This is just from linearizing the circuit using the first term of these corresponding nonlinearities. Then for this element 1, I have V1 of 1, and from this, from its nonlinearity, I calculate the additional current source. Okay, and for this second element, I mean, its nonlinearity could also be different, right? For E2, I do the same thing. I calculate the additional current source for it from V2 of 1. Now, in the second step, I use these two sources as additional sources in the circuit and calculate this. But every time I'm only doing linear analysis. Only thing is I'm adding more and more sources. That's all. Now, what is superposing? You will get the same thing, right? Because the analysis you are doing is of a linear circuit. Whether you do it with only this source or that source or both together, that is more a calculation thing. You could put all the current sources together and calculate, or do it one at a time, right? But the step 2 is completed only after you do it for all the sources and add up the results. You understand? Yeah. Right. No. At every step, what we are analyzing is only a linear circuit. Okay, we are just creating sources from the nonlinear characteristics. That's all. For linear circuits, superposition is valid. Yeah, that's right. So, but we have reduced the nonlinear analysis to linear analysis, stepwise linear analysis. This analysis, by the way, never gives you the correct answer until you go through infinite steps, right? Okay. So, it only gives you approximate answers, but it gives you better answer than doing only the step one and then stopping. That's all. Okay. But we are not analyzing nonlinear circuits at any step. We are only analyzing linear circuits. Nonlinearity of nonlinear elements appears as additional sources in every step. So, sources you have to calculate newly in every step. The sources are based on the nonlinearity. Analysis is of a linear circuit. In fact, it is the same linear circuit. Right. Any questions? I mean, we can't do it, we can do this. That's right. We can't do that, we can do this. That is, if you put the full nonlinear equation, we can't solve it. Huh? I don't know. So, let's say, where is that? Yeah. How would you solve this? I mean, this is not even a differential equation. This is an algebraic equation. How will you solve this? What methods do you know for solving nonlinear equations? Huh? What's that? Well, I mean, so that means that you're hoping that your circuit only has like plus 1 volt or minus 1 volt as the answer. No, that's it will have a, it's not a quadratic, right? It's a cubic, no. Yeah. Okay. No, because the other one you can't do at all, right? How will you solve it? I mean, if I say that Vi is Vp cos omega t here and I give you this equation, could you tell me like what the second order term is? See, this is to get some qualitative answers. It may not be exact, but again, if your weak nonlinearities, which means that the nonlinear terms are smaller than the linear term, it is okay, right? Whereas this one you can't solve at all. And this is like an extremely simple case. Whereas that method can work for any circuit. Okay, any complexity. Of course, there is always a limited complexity that you would handle by hand, and then after that you may go to symbolic simulators and actual circuit simulators and so on. Whereas this cannot be done at all. And then if I add a capacitor, I think we are finished. We can't do anything with this. Okay. By the way, do you know how to solve this? How would you go about solving nonlinear equations? You must have seen it in some maths class or no? What are the methods for solving nonlinear equations? You are not familiar with any? Yeah, what will you iterate? There are many. First, there is nothing that guarantees that you will find all solutions. One is what is called binary search. What he is saying that you assume that the solution lies between some 2 points, and then especially basically you will be solving. When you say solve, what is meant is that you find x that satisfies this, right? So one is if you find some x1 and x2, okay, where f of x1 is positive, f of x2 is negative, or vice versa, then you do binary search, right? Bisection method. Then you go to x1 plus x2 by 2. Okay, if that is positive, then you divide this side by 2. If it is negative, you divide that side by 2 and so on. So that is one possibility. So this will get you to solution. All this you have to iterate many times to get it. The other one is, have you heard of things like fixed point iteration or Newton-Raphson iteration and so on? Newton-Raphson, what is it? You assume this is f of x, and you assume some starting point, and you assume that the actual nonlinearities are tangent at that starting point, and then you find this. This won't be correct, so then you go to here, and then you find that it is tangent there. And actually, it's one of the fastest ways of finding solutions to nonlinear equations. There are many others. There is something called fixed point iteration. You have to rearrange this as g of x equals x. So if you do that, then you start with some x, you get some g of x. Okay. Then you take g of x. Then you keep substituting. So if it converges to, I mean, if it doesn't change from one step to another, that means that you've got g of x equals x. Right. There are many techniques. I think people have worked on it a lot. But all this is for calculation on a computer, basically. We can't do, I mean, you can't for a general case do this. Okay. And our aim is circuit analysis. In fact, this the 2-element toy example is not even what you would normally see. You will have maybe more elements, you may have a capacitor and so on. So in that case, you will have to do something more elaborate. Okay. In fact, the next assignment has one toy problem like this, but it is with some system which has some memory. That is, you have to do this Laplace transform business. Okay. Now, one thing I have to say is, of course, there are certain kinds of symmetric nonlinearities in which you have only odd order terms. Okay. In that case, this even order complexity is not there. You have g1x plus g3x cube. So the second step would just simply be this d3x cube, right? This the second order stuff is not there, and that is easier in some ways. Okay. So again, typically we stop after calculating the third harmonic. So you only need one step over. Any questions? Yeah, you have to, I mean, in a MOS transistor, for the classic long channel MOS transistor, you can derive it from physics, but you can measure the voltages and currents, right? And from that you can get it. For resistors and so on, all of them will have some nonlinearity. So you make measurements over some range that you think is reasonable, and then you get the nonlinearity. Okay. Any other questions? Okay then, see you all.